Good morning or afternoon, everyone. This will be our video on Thursday, June 4th. Excuse me, almost said May again. Here's the date here. So we've got our June 4th lecture. Since we won't be having an in-class lecture, and this will be a lecture on section 6.7, part of section 6.7, just involving our trig substitutions. So in class today on Wednesday, we just finish up trig integrals, what's going on with these powers of sine and powers of cosine. And so now we're going to see some extra applications of these trig identities. So as with our typical lectures, let me start off. I want to start off with a bit of the theory and some of the concepts behind it that we're going to use, and then we'll just go straight into a bunch of examples. And I want to make our examples as like an increasing order of difficulty. So the difficulty of the examples will get harder. Actually, let me just double check. Good. Microphone looks like it's working well. And so we can go ahead and get started here. Okay, so let's review the trig identities. The biggest one in this case is the Pythagorean identity. And we'll talk about why it's so useful. We were using this a lot today. We have our sine squared of x plus cosine squared of x equals 1. And of course, we can solve that for either sine squared or cosine squared. And so why is this useful? Well, we saw in these trig identities and these trig integrals, we were able to substitute powers of sine, even powers of sine or cosine, into the other sine or cosine, whichever one wasn't used. And that helped us make these u substitutions, or possibly at least reduce things down to something like a double angle formula that would help us integrate these powers of sine and cosine. With substitutions, we are actually going to use the right side to get to the left. And this is going to be useful because if you look at the right side, we have a difference over here, right? It's 1 minus sine squared, 1 minus cosine squared. And so it turns a sum or a difference into just a single expression, which is going to help us, especially if we have a sum or a difference under square roots. You will see these a lot. So let's write that out. So it turns sum difference into a single expression. Going to be useful for differences under a square root. Square roots, as we've seen so far, we kind of just need a single expression underneath the square root. Otherwise, we have to do a u substitution with everything that's underneath the square root, and then hopefully that the differential will substitute also nicely. But if we don't have that differential, we're kind of out of luck at the moment. And so in this case, if we have like a sum or a difference under the square root, we'll make these fancy trig subs, which we'll see here in a second, and then that will turn whatever's underneath the square root into just a single expression, which hopefully we can then take a nice square root of. So let's finish up real quick before we jump into an example of what I mean by that, just with the other trig identities that are going to come in handy, primarily because, well, I did say sum and difference over here, but this is just a difference. So the other Pythagorean identities, hopefully you remember, as I tell my pre-calc students, you only really need to remember this guy as well as the half angle or the double angle identity, because from this guy we can get many of the other ones. So the ones involving trigs, or excuse me, tangents and secants, all we got to do is let's divide this whole expression by, let's say, sine of x, or excuse me, let's divide by cosine of x. Let's just do that one, just because that'll give us a sum here. So if we start with our original Pythagorean identity, divide by cosine, we will get sine squared x over cosine squared x. Cosine divided by itself will just give me 1, is equal to, the right side will be 1 divided by cosine, which is just secant squared x. So the other identity that is very useful is tangent squared of x plus 1 is equal to secant squared of x. So again, what we have is something turning a sum of two different terms into just a single expression. Okay, and then of course the other identity, we'll write down the cosine squared x minus sine squared x equals cosine of 2x. I can now use the Pythagorean identity to substitute these guys in and solve. So we will have our two double angle formulas. So cosine squared, we'll have 1 minus cosine squared x equals cosine 2x. I'm just going to go through the algebra real quick. So this is going to be 2 cosine squared x. We'll have a minus 1. We can just add that over. And then divide everything by 2. So we'll have cosine squared of x is equal to 1/2 times cosine of 2x plus 1. As well as if you solve for sine squared of x, you'll get a 1/2 cosine of 2x minus 1. And let me just double check that one, make sure I didn't get the minus sign out of order real quick. So if we go back through the steps and now, so if I substitute 1 minus sine squared, we will have 1 minus 2 sine squared. So when I subtract the 1 over, and then I'll divide by a negative 1, and so these need switched. 1 minus cosine of 2x. Yeah, because we'll subtract the 1 and then divide by the negative 2 from that. So yeah, had those guys out of order. And I'm watching my video. Sorry guys, I'm off the screen. Let me change that real quick. So just to reiterate what I did there, I just took that same expression. I'd solved it for cosine squared. And then we can take the same expression and solve for sine squared. So let me box all those. Those will be our identities that we're going to want. And these two here, we really only need for these are like our end of problem type substitutions. And once we've done a lot of the hard substitutions with these trig substitutions, what we're left with, we might be left with sines and powers of sines and cosines. So just like the project that was done on Wednesday, these substitutions can result in trig identities with sines and cosines. So I just want to keep those handy just in case we have to do an integral of sine squared or an integral of cosine squared. As well as the two identities that I primarily like to use are these two here. I like this guy. And then this guy. Of course, there's other ones. Right, if I had taken the original Pythagorean identity and then solved for, divided by sine squared, we could get another Pythagorean identity involving cosecants and cotangents and whatnot. It's usually not as useful, primarily because of the minus signs that come up with the differentials. Really what we're going to see in these problems is we want to be able to turn a sum into a single expression or a difference into a single expression. And so it often doesn't matter which trig identity we use. We'll get the same answer, even though they might look different based on the end result. It might look different in terms of the answer you get, then you just need to do some fancy trig identities to get it look like a different expression. For me, philosophically, I just like to use these because the substitutions we make will be substituting sine in. The derivative of sine is a positive cosine. The derivative of tangent is a positive secant squared. So there's no extra minus signs floating around with these differential substitutions that we have to do. So on that note, these substitutions are kind of similar to u subs, in that instead of making u some expression, what we're going to do is make our substitution involving trigonometric stuff. So we're going to turn maybe polynomials into trigonometric expressions so that we can use these trig identities. And as such, we're going to have to keep track of the differentials in the substitutions as well. So let's start off with sort of the canonical example. This will be similar to one that was due on your homework on Wednesday. Where on Wednesday we had this problem where it said we first need to make a u substitution, and then the rest of the problem, the hint, they said recognize the answer as some sort of geometric identity. And hopefully everyone caught that, where it ended up being like a quarter of a circle. And you kind of just had to know, well, because this integral represents the area of a quarter of a circle, I know the area of a circle by the canonical formula of pi r squared. And that's what we know it is. Well, what if we don't know that formula? How do we do that? So let's give our example as, let's suppose we want to find the area of a quarter circle, and let's say the radius of the circle is 3. So we'll have our function for that is y equals square root of 9 minus x squared. Right, we kind of just take x squared plus y squared equals 9. So remember, this is our form of a circle, but the top half solving for y will give us this expression. And so 9 is the radius squared. And so that's our graph here. And we want to find this area. How is that going to be denoted by an integral? Well, we'll have the integral of 0 to 3, and I want just the area under the curve. So we'll just have square root of 9 minus x squared dx. So we know what the answer should be. So the area of a circle is pi r squared. So this area of a quarter of the circle is just going to be 1/4 pi times 9. Or in other words, 9/4 pi. Well, how do we do that now? How do we actually prove that the area of a circle is that? Where does that formula come from? So unless you're an advanced ancient Greek geometer, the best way to do it is through something like this, through some calculus and through our definitions of trigonometric functions. So what do we want? Well, I can't deal with this square root, right? As I was kind of mentioning before, whenever we saw some square roots so far, we needed to make a u substitution, especially if there was a difference underneath the square root. I cannot take the square root of both terms individually. Hopefully you guys are way past that, since this is Calc 2, and they probably graded you harshly on that if you did that in Calc 1 and definitely in pre-calc. And so hopefully you guys have gotten out of those habits, knowing that I cannot do anything with this square root. I can't simplify it just through simple algebra. So if we tried to make a u sub, though, and sub out the whole inside of the square root, u is 9 minus x squared, what would my differential be? The differential in that case would be something like 2x, negative 2x. But we don't have any x's outside to pair with that dx. So that's not going to work. Instead, what we want to do is use one of these identities here. And it's going to be a little bit more just because we have that 9 in there, right? I want to be able to turn, I have something like 1 minus, or I guess we should write out a little bit more general form, like a constant minus x squared. constant minus x squared. Well, that looks kind of similar to this. It's 1 minus sine squared. This is a constant minus now sine squared. So if I could make this x maybe something like a sine squared function, then maybe I can use this identity to turn the difference into just a single expression. And that would help me out a lot with this square root that's going on. So here's our idea. So if under the square root, let's say we had 9 minus, well, because that's a 9, I actually want 9 sine squared of theta. So this is just kind of thinking ahead. Why do I need these two constants to match? Because now I can factor out the 9. And now I have this 1 minus sine squared theta. And now this is just a product. And we'll just have 9 times 1 minus sine squared. Now we use that Pythagorean identity, and the difference goes away. And we just have a product there of some nice things we can square root. So this is our kind of thought process of thinking ahead. Let's do this and make sure we're formal and keeping track of all of our steps, especially with the differential. So if this is where we want to end up, well, what do I need this x squared to be? You can make the substitution by saying something like this. I want x squared to be 9 sine squared of theta. Let's use our new variable as theta. Okay, well, that's x squared. We want to be proper with it. So that's just saying our real substitution is for x. So let's say x is 3 sine of theta. And of course, I can arrive at that just by taking a square root of both sides. We only need the positive square root, since if I'm going to square it, it'll be positive anyway. And so if I make the substitution as x equals 3 sine theta, then that means x squared is going to be 9 sine squared theta. And that will plug in there nicely and give us this stuff over here. And the reason that I want only a substitution involving x is because we also need to substitute out our differentials there. So this is going to say that dx is, I take a derivative of both sides, is going to give me 3 cosine of theta d theta. And this is why I like to use that sine expression. Maybe some of you guys are kind of catching on that. This says 9 minus 9 sine squared. I could have just as easily used cosine, because then it would be 1 minus cosine squared, and I would get a sine squared there. It would still work out quite nicely. But what's the only real difference is that if I had a cosine here, while it would still work, the derivative of cosine is negative sine. So I just have an extra negative to deal with and keep track of. And for me, for the sake of keeping track of my work and not making minus sign mistakes, which everyone does, of course, even up to Calc 2, Calc 3, and for the rest of your life, you will make a minus sign mistake at some point in time. It just happens. To kind of mitigate those errors, let's just not even deal with anything where minus signs come up. So kind of as a general rule of thumb, anytime you see these constant minus something squared, I like to use a sign substitution with a corresponding constant to match. Okay, so let's plug this all in and see what we get for the integral. Let me move the camera here. We've got our integral of 0 to 3. So I've got 9 minus x squared is 9 sine squared, just as we planned. And then I've got my dx is going to be 3 cosine of theta d theta. So I can move the 3 out front of the integral because it's just a constant. The cosine has to stay in the integral. And if you want, you can put a parentheses just to be clear of where that square root is. And now let's go ahead and simplify. So what's this? We've got 3, 0 to 3. I can factor out the 9. 1 minus sine squared is what's left. Cosine is on the outside. we've got 3. This is square root of 9 cosine squared theta, cosine theta, d theta. I'm going to move to the right here to use a little bit more space of the paper. What did I do? I did not write the bounds. I almost saw that 0 with that top bound. Sorry for that. So bounds are still, oh, and actually I need to change those. One point I just forgot. Let's make corrections. I'm focusing on the hard stuff and forgetting all these minor details here. Why do we not want these 0s and 3s here, guys? So if you're in my class, you're probably recognizing these. Just as with U subs, these, the 0 to 3 were x bounds, right? And since I changed my variable, or my variable's theta now, we need to make sure that the bounds are corresponding to that theta. So just like with U subs, you can leave the bounds completely off if you'd like, do the whole problem, resubstitute back in for x, and then plug in the x bounds. Or you can just change the bounds to correspond with theta, which is how I kind of like to do it. So I'm going to go ahead and do that here. What are the appropriate bounds? We've got x is 3 sine theta. So when x is 3, the 3's will cancel. And when is sine theta equal to 1, you should remember, think way back to the unit circle. That's pi over 2. And the lower bound, we will have 0 for x. I can divide by the 3, and we'll just have 0 is equal to sine theta. And so theta is equal to 0 as well. Sine of 0 equals 0. So these bounds should be 0 to pi over 2. Sorry if that's a little illegible. I'll fix it in the next integral, though, for sure. So what do we have? We've got a 3 there. We've got 0 to pi over 2 are our bounds. And then square root's nice. I can square root of 9 is 3. Square root of cosine squared is cosine theta. Times this extra cosine theta will give me a cosine squared of theta. And then d theta. So what do we get? We've got 9 times the integral 0 to pi over 2 of cosine squared of theta, d theta. And this is why I wanted to give those half angle formulas. So since we have a cosine squared coming up, it's good to keep those handy. Let's see, where did I put my notes? Right here they are. So we go back to our note sheet and we see that our cosine squared is 1/2 cosine of 2x plus 1. So we can go ahead and make that substitution. Hopefully you guys did this on the project today. If not, I would say go back and check that just to make sure you're comfortable with doing those integrals. So my cosine squared is just 1/2 cosine of 2 theta is my variable plus 1 d theta. Okay, so now we've at least put this into a formula that we can now recognize. No extra powers of cosine, it's just a single power. We can do a u sub here if we'd like. Let's go ahead and pull this power of 1/2 out. And so we will have 9/2 times the integral of 0 to pi over 2 cosine of 2 theta plus 1 d theta. I'm going to go ahead and integrate that. If you guys want, do this as a u sub and do this in steps. Just as with the chain rule in Calc 1, you should be able to start doing these quicker and quicker and doing some of the steps in your head. And I know this is summer, and I know we just learned this like 2 days ago, but it moves fast. So try to keep up, especially with these basic just constants that are inside arguments. Hopefully you're kind of getting the hang of just being able to integrate them, just as we would with taking derivatives. Instead of just multiplying by that constant, where you're going to divide by that constant. So the integral of cosine is sine of 2 theta, and I need to divide by that 2. So multiply by 1/2 to account for that chain rule. Plus a theta, 0 to pi over 2 is how we want to evaluate that. These problems take up a lot of paper. I have to keep moving that. Let me move it up a little bit. That still looks pretty legible. It might give me some more writing and viewing space here for that camera. Okay, and so what's going to happen when we plug in our values? Well, if I plug in pi over 2, we will have 9/2 times, what is sine of pi, or excuse me, it'll be 2 times pi over 2. So it'll give me 1/2 sine of pi plus pi over 2. Sine of pi is just 0, though. And then we'll have minus, let's plug in the other bound first, and then we can just multiply through. What's going to happen when I plug in 0? Sine of 0 is 0 plus 0. So we'll just have 0 for that lower bound. Oops, not a theta, a 0. And so the only term that remains was this pi over 2 times 9/2, and we get then 9/4 pi. Exactly like we expected. So we kind of just proved and verified this geometric result that we had for a quarter of the circle. Okay. So hopefully that was clear and not too quick. Let's try to go through some examples. Oh, and I should mention, this will be a 2-part video. Unfortunately, I am having some issues with Zoom right now, and actually it's an issue with the hiring managers. They didn't put me in the system correctly, so I don't have Zoom Professional. So we'll have to do this in video in 2 parts once the timeout screen starts going down there. So I'll try to time it, hopefully make sure it's not in like the middle of a problem or something, but we'll see how it goes. Oops. Let's see. Just organizing my notes here. I do plan on putting some of these notes. I'll try my best to try to put my lecture notes online. I don't have a scanner myself, but if I can run into campus, it'll be easy to scan a bunch of them at once. Otherwise, I can try to use one of those phone scanner apps to put the notes to go along with the lecture videos, just in case you guys want them. Okay, so let's see some just generic types of integrals that you might see where these types of substitutions are going to come in handy. So we've got one example that is just the integral from 0 to 2 square root of 3 x cubed over square root of 16 minus x cubed. Oh, excuse me, x squared dx. And so the key thing we look for is we see a constant minus x squared term. In a square root. So that indicates trig sub. So I want to be giving you guys these pointers, right? Especially on midterms quizzes, midterms in particular, right? If we have a list of integrals and have you compute them, we may not tell you what technique you need to use, and it may not be clear. So the difference between Calc 1 and Calc 2 is, well, if you're taking a derivative and you see nested functions, boom, chain rule. If you see a product of functions, boom, product rule. You know exactly what to do. on Calc 2, when we're finding antiderivatives, it's kind of like we have these grab bag of tricks that we're learning. So this is our kind of third trick. We have our U sub, our integration by parts, and then now we have these trig substitutions. And we're going to keep sort of just adding tools in your tool belt, so to speak, but you got to be able to recognize when do I use what tool. So knowing when to use what tool can really save you guys some time. So anytime you see these constant minus x squared or a constant minus something squared, as we see more complicated examples, it's a dead giveaway that a trig sub is probably the best way to start or first thing to look at. We can, I mean, you may want to try to look at a U sub, right? We've seen a few U subs with square roots that work, but what happens if I make a U sub involving an x squared? Then du is just a single power of x. And here I have 3 powers of x. There could be some fancy things we could try to manipulate around with a trig sub here, or with a U sub, but for the sake of this section, let's stick with a trig sub and see how this is going to work out. So we've got 16 minus x squared. It's a minus, so we want to use something like 1 minus sine squared. But since that 16 is there, we want 16 minus 16 sine squared of some variable. We'll have our new variable be theta, say. If you want to use u's, you can use sine of u, or any variable will work. T's, often people like to use. Is that focusing? It's still legible. It looks a little fuzzy. Sorry if that's what it is. So this is what we want. What does that mean? What do we need to make x squared? So our x squared is then going to be 16 sine squared theta, which means that our substitution really comes from x equals 4 sine theta. And if we have that, then dx is 4 cosine theta d theta. And again, no extra minus sign, so that's going to be nice. Okay, so what's our integral become? Sorry, I was just getting lost in my thoughts there for a second. We've got our square root of 16 minus 16 sine theta, so squared theta, in our denominator, just as we like, because that's our complication to this integral. And now we've got this x cubed, which means I'm going to have to cube this guy. So this is just going to be 4 cubed is what? 2 to the 6th, which is 64 sine cubed. So I just cubed out this guy for our substitution of x. And then my dx is times another 4 cosine theta d theta. I didn't put the bounds in. Let's check our bounds here real quick. So 0 should be pretty easily. When x is 0, we'll have sine is 0. 2 square root of 3, you may want to do some work. When x is 2 square root of 3, we've got 4 sine theta. So if I divide by my 4, we get square root of 3 over 2 equals sine of theta. Where is sine of theta equal to square root of 3 over 2? So we just want the sort of like arc sine of square root of 3 over 2. So hopefully you guys, you remember your unit circle. If not, redraw it. This is going to be a 30, 60, 90 triangle. So let's say this is our short side. 1, 2, square root of 3. Short side is, this is pi over 6. This one's pi over 3. So we want sine of pi over 3 is square root of 3 over 2. So that's our upper bound there. I like to get those out of the way just because it's kind of just an extra point. Of course, the bulk of the work is doing all the algebra, the substitutions, and the integration. Okay, so let's see what we got. Our 64 times 4, what is that? So 64, you can even just write them out here. Let's write it as 64 times 4. It's a constant. We'll leave it out front for a second. We've got our sine cubed theta. We've got our cosine theta. We've got square root of 16 times 1 minus sine squared theta. And we got our d theta. Don't use calculators when you don't have to, right? Even if it's 64 times 4, do some mental math tricks just to practice. It'll help keep your brain sharp. I really want to emphasize that for you guys. I try to emphasize this for my pre-calc classes. A lot of the things people fail and make mistakes on Calc 1 and Calc 2 is all the algebra. So when you can, just try to challenge your brain with the easy stuff, even if it's multiplication. I know the numbers look big, but another reason why I didn't multiply them out yet is because we're going to have another constant coming out of this bottom, which might help simplify our calculation. So try to find those kind of tricks and challenge your brain to do so. 1 minus sine squared, I'm going to go ahead and kind of do my steps like this. So I know that's a cosine squared, and then I'm going to square root it all. So what are we left with? We still have a sine cubed in the numerator, cosine in the numerator. The denominator, square root of 16 is 4, and then that square root of cosine squared will just give me that one factor of cosine. And then I've got 64 times 4, and lo and behold, when we pull that 4 out, those two guys will cancel. My cosines will cancel, and we are left with 64 times the integral of sine cubed. And I got to put in the bounds still. I've been neglecting those, so my bounds were 0 to pi over 3 for all of these guys. Sine cubed, we did this one on the project today. So this one we can write as, let me move the video here. This one we can write as 64 integral of 0 to pi over 3. Sine squared times sine. And that sine squared we can turn into 1 minus cosine squared. So just to write out the steps real quick. I don't want to have to write out a lot of these steps. I do want to get through a lot of problems, which unfortunately means got to be sharp with all these algebra. And I can always help clarify some steps in office hours if you guys have questions. So we did that, and now we may have to do our u sub. So u is cosine theta. Du is our negative sine theta. D theta. We've got 64 times the integral of u squared minus 1 du. So I just multiplied that minus, which would flip the order of those guys. And now what are our bounds? Cosine of 0 is 1. Cosine of pi over 3 is 1/2. And now we finish the integral. We've got 64 times 1/3 u cubed minus u. Bounds between 1 and 1/2. So it doesn't matter, right? The 1/2 is smaller on top. Sometimes it happens, which is kind of a result of that minus sign flipping the order of the bounds in some sense. You can kind of think of it geometrically of kind of why the lower bound is now on top or the smaller values on top. And then we just plug in and evaluate as usual. So we've got 64 times 1/3 times 1/8 minus 1/3 minus that 64 is being multiplied by everything. Plug in 1, and we've got 1/3 minus 1. And now we should see the numbers working out more nicely. Yeah, I got to keep moving this video. Running out of space. And so let's go ahead and compute that real quick. So we've got 64 times 1 out of 24 minus 1/3. So 1/3 is 8 over 24. So we've got 1 minus 8 should give me -7 out of 24. minus 1/3 minus 1 gives me a negative 2/3 equal to, so of course that's positive. What do we got? 64 times 2/3 minus 7 out of 24. So 2/3, multiply that by 8/8. We've got 16 out of 24 minus 7. Gives me 64 times 11 out of 24. 24 is 8 times 3. So I can factor out an 8 from each of those. And so it looks like we get 88 thirds as our answer. So a lot there. I'm going to do a lot of these without having to plug in the bounds because that was just a lot of extra stuff. Really, I mean, the bulk that we want to challenge you guys with is, do you understand how to make these substitutions and come up with the correct integral? So let's try a few more. And that was actually one of the easier ones. Let's see, this was page 3. Let's do one with a sum. And let's see what happens when the constants don't work out as nicely. So this one's from the book, homework problems. Actually, I don't know if it's on the homework, but it's in the book. Section 5.7, number 3, we got an integral of dx over x squared square root of 4x squared plus 9. So again, our indicator is this guy, is something squared plus constant. Is under the square root. So it's an indicator. Again, we want to use a trig sub. But we want to use our other trig sub that we mentioned at the very beginning. This 1 plus tangent squared is secant squared. This is the identity. It turns a sum into a single term, which will help us underneath that square root. So same concept, but now we've got this extra constant to deal with. It's 4. Even if that wasn't, 4 is a nice perfect square, but sometimes if we wanted to be a little cruel, we could have had that as 5 or 6 or 7. If it was 5x squared, keep in mind 5 is still something squared. It's just square root of 5 squared. So it's just really the x squared that determines it's something squared plus a constant. So how do we deal with this? So what do we want? Let's write out some sort of steps on the right. Well, I have something squared plus 9. If it was 9 tangent squared of theta plus 9, then that's going to equal 9 secant squared theta, just because we can factor out that 9, and it would be 9 times secant squared. So if this is what we want, that means I need this 4x squared to be 9 tangent squared theta, right? I want to substitute this first guy here to be 9 tangent squared. So that way I can make use of this trig sub. So you can kind of start off with an expression like this. And again, let's just solve for x. So this is just x squared is 9/4 tangent squared theta. Square root both sides. Constant's not pretty, but it's not terrible. At least we don't have extra square roots in there. They give us nice square numbers. So 3/2 tangent theta. And then now once I've solved for x, we find the differential. So dx is going to be 3/2. Derivative of tangent is secant squared theta d theta. So that's looking a little blurry. Trying to play with the lighting on the camera. See if it'll pick it up. I think that's coming up the best. All right, let's keep going. So we've made our x's and our dx's. Let's just go ahead and rewrite our integral now. What do we have? We've got the integral of x squared is going to be this 9/4 tangent squared. So this is kind of the other nice thing about writing out each of these steps and solving, starting with I want this 4x squared equal to that guy. You also have a nice expression already for x squared, which often appear in the problems. Like a lot of these steps can often appear here. Sometimes I think in the last one, our x squared was in the numerator or something like that. We had an x cubed there. Okay, and then underneath the square root, we have our 9 tangent squared theta plus 9. And then our dx becomes 3/2 secant squared theta d theta. So let's pull the constants out. We've got a 3/2. The 9/4 in the denominator means I multiply by the reciprocal out front, which is back in the numerator. We've got a secant squared theta. I'll keep the d theta out front. We've got a tangent squared. And then this guy, we pull out the 9. It'll be 9 times the quantity, tangent squared plus theta plus 1, which gives me that 9 secant squared theta. And so what do we get now? Of course, these simplify. We've still got a secant squared on top. We've got tangent squared theta. And then, of course, we'll have another power of 3 in the denominator here. And then I'll have square root of secant squared is just going to give me secant theta d theta. We've got 2/9 integral of secant theta over tangent squared theta d theta. And let's see, what's the easiest way to go about doing this? Might be to turn it into sines and cosines. So the activity, the project for Wednesday, we had these trig integrals. I think most of them were all sines and cosines. Sometimes you can kind of play and find similar rules with tangents and secants depending on where they appear. The derivative of tangent is secant squared. And unfortunately, we only have 1 power of secant left. Derivative of secant is secant tangent, but I don't have a tangent in the numerator. So unfortunately, we can't just make a u sub outright from here. It looks like a better way to look at the problem might just be to turn things into sine and cosine. So let's keep our track of our constant. We've got the integral. Secant is just 1/cosine theta. I've got 1/tangent theta, which is going to give me cosine squared theta over sine squared theta d theta. So those will cancel, at least the cosines. And what are we left with? We're left with a cosine theta over sine squared theta d theta. And now, hopefully it's a little more clear. We've got to jump back to our first technique and some of the techniques what we saw in this trig integral project. I only have one power of cosine. That's my odd one, right? So let's let our u equal sine. So that way my du will cancel out that cosine nicely in the numerator. And so my integral becomes 2/9 times the integral of 1 over u squared du. Integrate, antiderive, and that'll just give me a negative u to the -1 plus a constant. So right, derivative of u to the -1, that minus will cancel that, and it'll give me a -2. And now we just got to trace back all the steps. Let's do all the back substituting. So u was sine, so we'll have a -2/9 times 1 over sine theta plus a constant. And then sine theta, oh no, what do we need to do? We got to go back to this point here, because this is where we made our trig substitution. But there's no signs appearing there. Sorry, I'm fidgeting there with the button. So what do? Think way back to your pre-calc days. This is the draw triangle. It's often the solution whenever you're stuck in kind of like a trig algebraic situation. It always helps. Draw triangle. Let me do that here. Let's try and get some space. So I just want to leave some space to leave the answer here. Draw triangle. Here, let's use pink. Let's get that highlighted. So our substitution was that x is equal to 3/2 tangent of theta. We have to work backwards and solve for theta, essentially, or solve for tangent theta is probably the easiest way to look at this. So really what we have, because we need to back substitute for theta, tangent of theta is equal to, let me make sure I got that constant right, it is 3/2, yep. So tangent of theta is 2x over 3. What does that mean? That means we can draw a triangle and let's say this was my angle, right? Theta is our angles, and tangent of theta should be 2x divided by 3. So tangent of theta is opposite over the adjacent. So this is just a triangle that says tangent of theta is 2x over 3. And now we use Pythagorean theorem for the other side. So hopefully this is coming back to you way back from those pre-calc days. So we will have, let's call this c. C squared is equal to 2x squared plus 3 squared. So c is equal to square root of 4x squared plus 9. And that should look familiar. Very often how these work out is that side was kind of like the hidden side of a hypotenuse geometrically, was really what's going on. And so if that's my c, square root of 4x plus 9, sorry for squeezing that in there. Now we just want to compute, I have in my original, or my answer that we were trying to back substitute for, we had -2/9 times 1 divided by sine plus c. And so we'll have -2/9 1 divided by sine. So sine is going to be opposite over adjacent, 2x over square root of 4x plus 9, x squared plus 9, excuse me. Got that squared there. So 1 divided by sine is going to be hypotenuse over the opposite. So I'm just going to go ahead and put that in there. So square root of 4x squared plus 9, all divided by 2x plus c. Whew, that was a lot. Let's clear up those constants. Minus 2 square root of 4x squared plus 9, all over 2x plus c. And 2's will cancel. So square root of 4x plus 9 is x squared plus 9 over x, negative out front. Okay, let's see. How long has this video been? I hope it's not been too long. Some of these problems can take a while. And unfortunately, it doesn't look like Zoom is neither giving me a time signature, nor is it kicking me off. So for some reason, it hasn't kicked me off of this session, probably because there's no one joining and I'm simply recording a video. Let's recap real quick. This happens a lot. Trig subs are very useful for whenever we see a sum or a difference of a squared term plus a constant or squared term minus a constant underneath a square root. We often have to do some manipulations with the constant. So sometimes it helps to think ahead, to think that, well, based on the constant I'm adding, what do I want the polynomial, the actual powers of x squared term to be? And we can use that to make our substitution. Once you make the substitution, it is just a bunch of algebra. Remember your pre-calc, keep track of all the constants, keep track of your trig identities, your simplifications, and it should simplify into something much easier that you can do as an integral. You often have to use a u sub once you get there. Again, extra steps, and then you have to go back substitute once you're finished. If you end up with a different trig function than what the original substitution was, right? Our original substitution was a tangent. Then you have to use a triangle to figure out the corresponding sides is the easiest way to figure out and how to back substitute that. These problems can get essentially one step harder. And the extra step is remembering completing the square. So I want to put one of those. I hope this video is not too long. I do want to at least get started on one of those and point some of that out to you guys. And actually, it comes to mind that there might be a, no, there's a third substitution. So I mentioned if we have constant minus an expression squared, oh, sorry, that video's got my desk here. I swear, my desk is actually clean. It's just the enamel's kind of wearing off, so that's what you're seeing on that video there. Let's do one more. Let me pick out an example here. Yeah, it's just an old desk. I need to like have it refinished or something. Yeah, so sometimes you have to complete the square to do these guys. And it can get messy. Organize my notes here. This is 4. So I'll give you the example. I'm actually going to modify the example real quick just to give you the other trig substitution. So I haven't fully thought this one through. It may not work out precisely. We may not be able to do some of the final integration steps. I just want to tell you what to look out for in these types of problems. So at least to get you to that like last step of what substitutions you should be looking for to make it look simpler. So here's our problem, x squared minus 6x. This one's different. What's our complicated expression here is that I do not have x squared minus a constant. Instead, it's x squared minus 6x. So in this type of situation, we need to complete the square. So what are we looking for here? Again, I can't use a u sub because if I set u as x squared minus 6x or even just x squared, there's nothing on the outside that will substitute out the dx. So I still have something squared. I still have something squared minus a something, and that isn't going to play nicely underneath the square root. So how do we complete the square? We got to work underneath the square root since that's where everything is. Remember, we take the middle term, the linear term, so we've got a minus 6x. Take that constant, 6, divide by 2 gives me 3, then square it. And we get 9. We're going to add 9 and subtract 9. So I haven't changed anything, right? Algebra is all about not changing the expression. Unless you have an equal sign, then you're doing things on both sides of the equation. Without an equation, we have to keep the exact same expression, just make it look different. So I add 9 and subtract 9. No change, just looks differently. And it looks differently because I can group these two terms, or those first three terms. We've got a square root. This square completes to x minus 3 quantity squared minus 9 dx. And now it looks more like something that we have previously done. This is some sort of function squared minus constant squared. And this is a giveaway that we want to use a trig sub. So there's one more expression that we want to use, or one more trig identity that we want to use that I forgot in the beginning. If it is constant minus the function, we can use 1 minus sine squared, 1 minus cosine squared to get rid of it. In this case, the function comes first. So what we want to do is use that tangent, except we just want to solve it slightly differently. We want to use this guy, except we can also write this as tangent squared x is secant squared x minus 1. This is kind of why I forgot it, because it's essentially the same thing, but it is in many ways a very different context that you will see, because here, what are we doing? We're turning a difference into a single term, but in this case, the function comes first. It's function minus constant and not constant minus function. So we want to use this identity to simplify things. So let's write that out here. So we want secant squared theta minus 1 is tangent squared theta. Okay, but we've got these constants in here, so let's think ahead. What do we want? Well, this constant is going to kind of replace this 1. So what do we want? We want 9 secant squared theta minus 1, or excuse me, minus 9, because that's going to give me 9 tangent squared theta. Sorry for my writing there. So we can just make that substitution. Even though this x minus 3 is there, I just want that x minus 3 squared equal to this guy here, 9 secant squared theta. So if I make that substitution, then this x minus 3 squared will give me that. I'll still have the minus 9, and I can simplify it. So that's my forward thinking. What's our substitution then? Well, now we just kind of follow similarly. We have to solve for x. So if I square root both sides, nothing fancy, and then solve for x. I have a plus 3 there. That plus 3 might play a little difficulty at the very end, but in terms of the differential now, it's not going to matter much. So derivative of secant is secant tangent, and the 3 will go away. So that's our formal substitution there. Now when we go ahead and make it, well, I already have this expression. I designed the substitution here so that x minus 3 squared is 9 secant theta. So we'll have square root of 9 secant squared theta minus 9 times my dx, which is 3 secant theta tangent theta d theta. Okay, and so now we can substitute, or excuse me, use our trig identity and simplify that guy. We will have 9 times secant squared theta minus 1. We've got our 3 secant theta tan theta d theta. We'll substitute that. Secant theta minus 1, so that square root of 9 gives me a 3, times that 3 will give me a 9 total constants out front. Square root of tangent squared will just give me 1 extra power of tangent theta. So I'll have tangent squared secant theta d theta. And again, this is one of those situations. It looks like, right, derivative of tangent secant squared. Derivative of secant is secant tangent. So it doesn't look like a great substitution for those guys. Let's turn things into sines and cosines. Tangent squared is sine squared over cosine squared. Secant is 1 over cosine. And actually, it looks like this one we probably may not be able to finish up. Normally, as we saw with the trig integrals, we'd like to have the odd one in such a way that I can pull out one of those, but because it's in the denominator, it's not going to work. So this was kind of just a caveat of, I changed this problem on the last one. The way I originally had it was 6x minus x squared. And if you do it that way, then you can use a sine or a cosine substitution, 1 minus sine squared, and take advantage of that Pythagorean identity. But I wanted to flip it just to illustrate that sometimes we have to use this secant squared minus 1 identity. So just because I didn't cook up the example ahead of time, we kind of end up with some sort of stuck thing where we can't finish the integral. Maybe if you guys have questions, I'll try to do an extra example like that in the future. But hopefully the techniques are clear. So once you get here, right, if I modified the x's out front and cooked it up in such a way that this would have given us a nice expression, we should then be able to do a u sub or something to that effect to integrate it, and then just go through all the steps of back substituting like we did in the last problem. Our key steps here, though, were I didn't have a complete square. There was this extra x. And sometimes you could see some other examples. So let me take a look at my example sheet. So these were some of the examples I was looking at of trying to get through. There's like this example here. That's a 4 there, where we've got y. This was in the book 5.7, number 11. Y times square root of 6 plus 4y minus 4y squared. So again, the 6 plus 4y plus 4y squared is kind of a complicated expression. The first step is to complete the square. And then once you complete the square, you can make your substitution based off of that. where sometimes whatever the completed square part of that is, you have to use for your substitution to get it into the form you want to use that type of identity. So hopefully that's clear. If not, please feel free to ask me tomorrow during office hours. This won't be on the quiz tomorrow, or on Thursday, I guess I should say. On June 4th is our quiz date. But the quiz will be over USub and integration by parts. And so this will appear on the following week's quiz. All right, hope that helps, and I'll see you guys tomorrow afternoon or Thursday afternoon.